back, so I'm assuming. I'm Praisner. I'm from Dr. Chen's lab at Stony Brook, and today I'm going to be talking about the effects of thermal habitat and other environmental drivers on striped bass growth in the Hudson. So, also another note, they have an ancient version of PowerPoint, so I didn't make my slides look terrible, but you know. The objective for my study was to look at what proportion of variability in length at age 1 for striped bass in the Hudson can be explained by water temperature and other environmental drivers. So some kind of sub-objectives to get me there were first examining temporal changes in length at age 1, and then developing temperature indices, DO indices, and NAO, or North Atlantic Oscillation indices. So all of these environmental variables were put into a generalized additive model, and then I went through a model parameterization and selection process with these environmental variables as the predictors and that median length at age as the response variable. So where did these data come from? They came from the striped bass sampling program. If you've been in here, you've already heard about the Hudson River Biological Monitoring Program, but this is a survey program with a really long time series from 1974 to 2016. This was just a quote-unquote side project, but it was a really extensive sampling effort. So this program was conducted from 1984 to 2016. They only sampled in the Battery region in the upper New York Harbor, so in this little box there. And the survey was targeting age 1 and age 2 striped bass that overwinter in this area. The survey had consistent methods starting in 1988. So for my project, I have 28-year classes with great median length at age data. Sample sizes were really large from this survey, so over this time series, over 500,000 striped bass were measured. So we have lengths for over 500,000 bass, and then a stratified random sample of the catchers taken. So for each year in this survey, we have 3,000 to 5,000 aged fish. They were aged through scale collection, so older ages are not quite as useful since they may not be as accurate. And then for just age 1 fish, we have 1,000 to 3,000 fish per year. So again, huge sampling effort. And this was conducted only in the winter since we're targeting overwintering bass. So that must have been really fun to be out. And they also collected water temperature data associated with each tub. So what we get from that is a great look at striped bass length at age from 1988 to 2015 year classes. That's on the x-axis there. Then on the y-axis we have total length from 0 to 450 millimeters. And there's nothing like crazy, nothing jumping out at you. It's not like we're seeing them get bigger every single year. But I would like to draw your attention to the fact that these bars in the middle, of course, are the median value, and it can have a huge range between years. And again, these are large sample sizes, relatively normal distributions. The confidence intervals for these, when you look at mean values, are very narrow, like just a few millimeters. So these are a pretty good estimate of our median length at age. And I'll draw your attention to the end of the time series here, just between 2013 and 2015. Those median values are almost 100 millimeters apart, which to me is a really big difference. So of course, that makes us wonder why. So to answer these questions, I first had to create an integrated temperature index. So since this SBSP was only run in the winter, we only have water quality data for the winter from that program. So using the water quality survey, this is a main survey as part of the HRVMP, I kind of combined those water quality data with the SBSP water quality data. So the beginning of this time series for each year class will kind of track striped bass movement through the river. So in red, we're seeing the water quality survey data over here. So we're looking at the region where striped bass are spawning and then drifting down the river during their year 0, and then overwintering the Battery. For their second summer of life, since they're caught at age 1, again, those data are aggregated over this portion of the river. So it might not be exactly where they are, but it's at least a proxy for the surface temperature that they're exposed to. And so what I'm showing you here is basically that summer, late spring, early fall temperature data are aggregated over river miles 12 to 152, so that is literally just averaged over the entire region. And then these winter water quality data are only for the Battery. This is also because the Battery wasn't sampled, in this main water quality survey. So the spatial and temporal coverage don't really line up, so that's why I created this integrated temperature index. So what we get from that is this beautiful temperature index where the red points, of course, are the water quality survey, the blue points are striped bass sampling program, and the surface temperature over here is from 0 to 30 degrees Celsius, and you're along the bottom. You can see that they don't match up perfectly. The water quality survey was like on a year-by-year basis trimmed to kind of fit between years of the striped bass sampling program, so there's no temporal overlap between these surveys. Of course, we still get some gaps, and it may look like they're overlapping in this graph. That's just because it's squished together. We get a few gaps, but overall, really great coverage, all things considered. So if we look at one single year class, we have to break that time series into each year class. And this is just an example for the 2000 year class. It's a pretty average one. I didn't pick the nicest looking one, but I think it looks pretty good. So here we have striped bass are hatching sometime in May, and then we have their exposure to the water quality survey program. So that's these temperatures here. We're covering the summer. Sometime in early fall, we transition to this striped bass sampling program where they're in the battery, and then back into the water quality survey. And then November 1st, they could have been caught in this survey, so that's where our temperature data stop. So again, I was pretty shocked to see how nicely those two surveys come together. And for each year class, I then fit a GAM, which is this red line here, to those data. And GAM fits were very high because, as you can see, we have a really great pattern there for almost every year class. And using this GAM, you lose some of the extremes, some of the peaks and troughs, but that's okay because I used it to develop this cumulative degree day index where we want kind of an average value of daily temperature. So since we don't have temperature observations for every day, you use the GAM fit to predict a daily average temperature. To create this index, you take that daily average temperature minus the base temperature for every single day in this time series, and then you sum them together, and only the non-negative days are summed together. So it shows us cumulative exposure to temperatures above some threshold. So if we look at 20 degrees, which remember that for like 2 minutes from now, it's all this area where the red line is within this box. That's what's added to this index. So I created 6 cumulative degree day indices. These are at 5 degrees Celsius intervals, plus the highest one I could construct with no 0 values for year classes. Then I created temperature minima and maxima indices without that fitted line, because when you have that fitted line, like I said, we're losing some of the extremes. So I created the average of the highest 5% of surface temperature observations, the average of the lowest 5%. Sample sizes were really high again for this, so we have about 3,500 temperature observations per year class. So we're taking somewhere around 200, a little less than 200, and averaging them to create these indices. I did the same thing for DO. Sample size is still high for DO. This is only covering water quality survey data, so late spring, summer, early fall. But that's okay because that's when we're expecting to see the lowest DO values. So we have a low DO index. And then I created 3 NAO indices, these 3 here. So a lot of studies will lag the NAO by 1 year to kind of examine its impact in the future. So I created a 1-year time lagged index from NOAA. You can get all of these data. They have this index value for every day. The 1-year time lag index is the average of every day in the time series for that year class. Then there's an unlagged index, which of course is the actual day. And then there's a 1-year time lagged winter index that's looking at the winter before. So with all these parameters, unfortunately, you can't just throw them into a GAM. So to select which predictor variables were in my initial model, which is how I chose my final model, I looked at their correlation coefficients to see which are too highly correlated to include in this model together. So all of the surface temperature indices were very highly correlated, which also kind of justifies my arbitrary 5 degrees Celsius choices instead of like trying to find something more biological. And these two, 20 and 25 degrees Celsius, unsurprisingly, had the highest correlation coefficient with length. But I did not just choose 25 because I had this highest coefficient. When I put these indices in their own separate GAMs, just with length, CDD 20 performed the best, had the lower AIC, the better model performance. So that's what's included in this initial model. When we look at surface temperature minimum and maximum, unsurprisingly again, CDD 20 and max temperature are highly correlated, so max temperature was not included. And then minimum temperature was not highly correlated, so this is included in this final model. Low DO index is included, no high correlations. Same thing with NAO, but I wanted to choose one index. So after examining individual models for NAO, the best model was actually with that 1 year time lagged index. So it was not the winter index like I suspected it would be. So from all of this, we get this lovely table showing this is our initial model, and these are 2 more models where I performed backwards elimination. So you remove the least significant predictor variable, and here, of course, we have length as the response variable. In this initial model, we have a smoothed cumulative degree day 20 index, a linear low DO, a linear minimum temperature, and a smooth NAO index. So for all 3 models, effective degrees of freedom are low enough that we can kind of assume that there's not overfitting going on here, and we don't have that many parameters to begin with. And then when you look at deviance explained, GCV, AIC, and R-squared adjusted, one model stands out for all of them, and that's this one here. So deviance explained is highest, GCV and AIC are lowest, which is what you want for a better model. And then R-squared adjusted is also highest. So removal of this North Atlantic Oscillation Index down here did not significantly improve this model. So just to kind of recap, since we're getting into all of the model parameterization, this final model that was selected, we're predicting median length at age 1 over this time series with a smooth cumulative degree day 20 index, a linear low DO index, and a smooth North Atlantic Oscillation Index. And again, that's that 1 year time lagged index. That's the year before each year class. So this model was validated with k-fold cross-validation. It performed well, but it's maybe not the best cross-validation method, so I'll be exploring other methods as I finalize these data. But what we saw was what you would kind of expect to see, but it's also really cool to still see it. So increased water temperature, so an increase in this cumulative exposure to degrees Celsius above 20 degrees Celsius were associated with an increased length at age. This is, again, in a non-linear relationship, so the higher the cumulative degree day index, the more impact it had on the length at age. And then lower DO was associated with a decreased length at age with a next linear relationship. And NAO was not significant in this final model, but I chose to leave it in because of the results I just showed you in the previous table. And it had kind of like a weak correlation with higher values associated with increased length at age. And just a reminder, a positive value of NAO, so a higher value in this index, kind of is showing us that you're more likely to have a warmer, milder winter in the Northeast US. So again, it's what you might expect to find. So implications for management are many. This is really great because if you notice that R-squared adjusted value, 52.3% of our variability in length at age 1 was explained solely by these environmental drivers. And the Hudson River, as other people have mentioned, is really key habitat for early life history processes for striped bass. It's where they spawn, it's where they have this juvenile overwintering habitat, often for the first few years of life. And we know the Hudson isn't, changing in this nice linear fashion, but it is still increasing in temperature over longer time scales. And of course, as temperature continues to increase and DO and NAO values will change, they will be affecting striped bass growth. And we've created this nice look at, an actual quantitative look at all of this using a really long time series and really large sample sizes. So these are just my acknowledgements. I'll let you read them yourself, and then I copied Steph's idea. So if you want to scan the QR code, you can see the rest of our HRBMP data and what the program was about. Thank you.